Okay. If people have questions, please just like use the raise hand feature, put it in the chat, um, so we can unmute you and let you ask a question. Let me start. Let me start so people have a little bit of time to think of one. If there is one thing you're looking forward to the most in the like development this year or like in the short-term future, which would that be? What is the one thing you were looking for all the time and it now seems to be in reach?
Oh, well, that's a good question. So I would say that the one thing that I am most looking forward to that seems to be in reach is that we're going to have a uh, robust ability to target using OpenMP and other mechanisms, accelerators from many different vendors. And I I know that's not one thing exactly, but it's really a whole bunch of different pieces all coming together, and I think that's really pretty important. So um, the way I see it, we have support for CUDA and HIP and SICL, which are the sort of primary programming models that are being from NVIDIA, from AMD, and from Intel, in addition to having OpenMP support. And the thing that I think is important that on which we're making good progress, and Johannes is really part of leading this effort, is that you know we are, how should I put this? LLVM is not only supporting parallelism, but is becoming aware of parallelism, right? So is getting to the point where we have an infrastructure that enables the optimization of parallel programs, and enables tooling that processes parallel programs and can be aware of the parallel semantics there. And this is very important because we have traditionally had a lot of problems in this regard, and they've manifested in two ways. So one is that we really haven't been able to allow users to employ abstraction around their parallel code because the abstraction penalties are very high. So because parallel constructs were kind of directly translated into runtime calls the optimizer didn't understand, it was very difficult for people to refactor their code. They couldn't pull things apart and put them in different functions, even if logically that's where they belong. They really had to program in a way where they were very aware of exactly how the code was translated into parallel, how the parallelism was implemented. Um, and one of the things I'm really excited about is that we're getting to the point where that's will be less true. I mean, there's always some extent to which that will be true, but we also should allow the compiler to help users organize their code in a way that makes sense to them, and then optimize the code by combining parallel regions or removing barriers or doing other things like that that are really important. And another thing that I will particularly point out is that this has been particularly problematic for accelerator code targeting GPUs, because a lot of the lowering decisions were made in the front end traditionally, and that meant that users had to be very careful precisely how they arranged and typed the pragmas and other directives in order to get good code to come out. And I think that we are now within reach of having an infrastructure which is more robust in that regard, that enables the optimizer to understand more what's going on. and will allow us to not only support parallelism across all these different vendors, but do so in a way which is much more, ergonomic, right? Which is more robust to source code changes and really allows users to concentrate more on the code than algorithms they want to write than on exactly how they have to arrange the code to get the right, magic incantation to make the compiler do the right thing.
I really thought you would say flying. Okay.
Now see that's an interesting point, because I am really excited about flying, but it's not the thing I'm most excited about. But I think that one thing that I like about, well, there are two things I like about flying, right? So one is I like the community aspect of it, right? We have a number of different vendors who are contributing to flying and are designing flying, and will be able to use it shortly. Flying is also new at this point, right? So it's going to take a lot of work to get it to a point where it's really robust. And so I'm very excited about that. I think that work is going on now, and obviously I hope we can get that to a point where it's really usable as quickly as possible, because we have users who are really looking forward to that capability. But that's that is going to take some time, and I think the thing that most excites me is when we have the capability to make something that is robust, that people will really not only use, but they can smile when they use it. So there we go.
Sounds good. We have a question. Toby has a question. Toby, can you ask yourself?
Okay, sure. I was trying to understand what you were explaining, the fact that merging LLVM IRs for link time optimizations and running a single pass is not scalable, and the thin LTO is. So I'm trying to understand why it's not scalable, and I feel like you have more view of the whole program when you merge the whole IRs together, and you could have like a lot of inlining going on or whatever. So I'm just trying to understand why it's not scalable and the thin LTO is. And also I would like to get your opinion about link time optimizations and resources that could be like helpful if you're like interested in link time optimizations and LLVM. So yeah.
Okay, great. So going backwards, if you're interested in learning more about this, then so there is a web page as part of Klang's documentation that talks more about the mechanics of how you enable things and use it. There are also several good talks at the LLVM developers meetings, which are on YouTube, and I encourage you to watch. I will briefly explain the problem of scalability. So normally when you compile a large application, one of the things that you do is you use a tool like Make or Ninja or whatever you use, and it will compile many source files in parallel, right? So you have 60 cores, and I run make-j60 or whatever command you like to use, and I can compile 60 things at a time. Now, in traditional LTO, problem is that LLVM is not internally threaded. All right, so when you do link optimization, the linker loads up all the stuff, and it puts everything in one LLVM IR module, and then it starts compiling it in serial. So not only have you given it a large amount of things to process at once, which of course have to be all in memory at once, so it takes a huge amount of memory, but it's processing it serially. So it's going to be at least 60 times slower than your make-j60, but it's at least that, right? Because you've given it more to do, right? There's more inlining it can do, and so on. So it's actually going to do more. So it's actually more than an n times slowdown when you use that kind of technique. What the thin LTO does is it enables you to use all of that parallelism, right? Because each of those IR files, the bitcode files, are processed in parallel. It's just that they have the ability to load things from the other files as needed in order to enable inlining and the like. So is that as powerful as actually just loading everything up in one module? It's not, but it does give you a lot of the benefit and does so in a way which enables compilation in parallel.
Okay, that makes sense. Thank you.
Sure.
So we have another question from Alistair. You want to ask it yourself?
Yeah, sure. So I know there's been a lot of different projects kind of adding different types of parallelism to LLVM. Zapier is the one that pops to the top of my head. They do like fork join stuff. I'm kind of wondering more like what sorts of parallelism are going to be added to LLVM in the future, and kind of like what like of the various projects that are out there are kind of getting into like the main branch of LLVM.
Okay, that's a great question. So first, I will preface this by saying that adding parallelism in LLVM is hard in some senses and easy in other senses. So one challenge with having parallelism in LLVM is that you have to, like, however you're going to represent the parallelism, presumably if you're talking about adding parallelism to LLVM, you're talking not just about the ability to have arbitrary function calls, which of course is easy, but the ability to have the optimizer understand something about those and then, based on that understanding, transform the code in useful ways. So, Tapier is one approach that's originated from the research group at MIT, and the goal was to enable LLVM scalar optimizations to kind of naturally apply over parallel code that will naturally give you certain kinds of optimizations. It's tricky, though, to enable this kind of support because you really have to make sure that the semantics are well integrated and that you have a good, well-defined rules for the way that other transformations can and should transform and analyze code. One approach that has been followed, and this is a sort of a traditional approach in LLVM, is to have runtime calls that are in the IR. So in some sense, they look just like regular function calls, but they're special in the sense that certain pieces of the optimizer understand what they do. And so, this has been true for, say, calls to malloc and free and new and delete and so on, for optimizations that are relevant there. And we can follow the same approach for parallelism using OpenMP or any other system that uses runtime calls. We have developed some extensible systems that enable you to do certain kinds of optimizations over these kinds of calls and so on. Now, beyond that, within LLVM, I don't think we have any definitive plans. I think the Tapier work is interesting. But I will also say that, of course, MLIR is now part of the LLVM infrastructure. And one of the key design goals of MLIR was to enable dialects that explicitly represent parallelism. And so a lot of the recent work inside the LLVM umbrella in representing parallelism has been occurring on the MLIR side and not on the LLVM side. So there are LLVM dialects that represent GPUs and parallel execution and affine loops and all sorts of things that have various degrees of being able to represent parallelism of different kinds. And applications are using those dialects, performing optimizations there that are parallelism aware, and then lowering down into LLVM, which is making more conservative decisions around parallelism, but is doing all the lower level compilation.
Okay, and we have one more question from Yi. Yi, unmute and ask yourself.
Oh, so just read my question. You mentioned tooling including sanitizers and X-ray. To use them in HPC needs to scale to at least 1,000 MBR ranks. That means both collecting and post-processing, including visualization, needs to scale and be usable for application developers. So how ready they are in that scenario?
That's a great question. So many of these tools are, how should I put this? I would put them in the category of minimally usable. So in HPC environments. So you can take something like address sanitizer and you can run it at scale. And what you can do with that is allow your code to crash and exit when it actually hits the memory overrun or use after free or what have you. And then you can look at the log files that come out and figure out where that happened and so on. You have the traditional problem with things that print stuff to standard error, which is that if you have 1,000 ranks printing something to standard error, it all gets kind of jumbled up, and you have to deal with that. But I mean, in practice, it's better than the alternative. It's not great. And one thing that I think would be really nice to see is a specific effort on scaling these tools to, specifically enable larger scale execution. So, we actually did some work at Argonne a few years ago as a summer project where we made some enhancements to the profiling gathering infrastructure in compiler RT. We did some experimental work that integrated with MPI. We also just added some support for making sure that the file names could depend on the process ID and as well as the host name and so on, so you get out separate files. But that work definitely, I think, needs to continue to make those kinds of capabilities more useful at scale. That's definitely true.